All right. Welcome back, everyone. Happy Friday. We are going to pick up where we left off, talking about discrete time channel models. Um, I will note that I posted problem set number 4. I have not posted a due date yet, mostly because I'm still grading problem set number 1, and I feel like it's kind of irresponsible for me to ask you for more things before I can even grade the things you've given me. So problem set 4 is available should you want to start on it. Once I post a due date, the due date will be 1 week after that date. Okay? So you will have at least 1 week to work on it. Okay. That's my promise to you. And I apologize for taking so long to grade your problem sets. But, work. Okay, so let's talk about PowerPoint. Where'd you go? There we go. Okay, so setting the stage once again, this module is titled OFDM, but rather than jump straight into OFDM, I thought that we should take a little time to appreciate some of the problems that OFDM promises to solve before just laying it all out there. So one of those problems is if your channel is distortive, that is, and there are multiple ways that a channel can distort signals that are put through it. But the one that we are going to handle right off the bat is what happens if it is not memoryless. So the picture, the big picture, literally from last time, was that all of this pulse shaping and additive noise and all that stuff that happens between discrete symbol generation on the transmit and the thing that we need to decide what was sent on the receive, that all can be kind of black boxed together into a discrete time system. And if you do that, then we can express the output of that discrete time system as the linear convolution of the overall channel. And I'm going to put channel in quotations here because technically speaking, this H encompassed more than just the physical channel. It also encompassed the pulse shaping and the pulse unshaping. This is the overall channel, quote unquote, impulse response. And these are the symbols. And strictly speaking, they're the past symbols between the current time n, n-1, n-2, n-3, all the way back to n-L, where we said that capital L was the last tap of the channel impulse response, assuming that it's FIR. And the other thing is that we called this discrete time sequence the noise, but it's the noise once acted upon by the receive filter. Okay. But since if we assume that the noise is white, then if we do linear and time invariant operations on samples of the noise, the resulting samples will also be Gaussian. Because if you take linear combinations of Gaussians, you get Gaussians. Okay, and then the last conclusion from this analysis was exactly that, is that at time n, the signal that we need to decide what was sent, so the z of n, has multiple symbols inside of it. It has the symbol that we want, S sub n, but it also has these other guys. And clearly, the shorter the impulse response of the channel, the shorter this list becomes, and somehow the easier it is to tease out what was sent. Right? In the limit, we have the memoryless channel, in which L is 0, and then we're good. There's no intersymbol interference. There's still noise, but there is no self-interference. Okay. Any questions on where we just came from? All right. And so now the challenge is...
I did have a question.
Okay.
Sorry. So SM, is that a function or is it a magnitude? And as it gets farther away, it'd be a different type of magnitude?
Great question. So the notation here leaves a lot to be desired. S sub n, you should think of as the nth symbol. So in QPSK, so a sample of this would be e to the j pi over 4, comma, e to the negative j 3 pi over 4, comma, e to the j pi over 4 again. And so this is going on and on in both directions. Right, so what I'm doing is I'm pulling constellation points out of here. And so this might be at n equals 0, n equals 1, n equals 2. But we're assuming that it goes endlessly in both directions.
Okay.
And then, yeah, every other discrete time signal on this slide has the brackets to indicate what time is. And then for whatever reason, your textbook puts a subscript for here. And I mean, there is a good reason for this, is that this signal is special, right? It is the thing that we are transmitting, and everything else is kind of being done to it. So I understand that, but at its face, it does mask the fact that it's actually a discrete time signal, just like all the others.
Okay, that makes sense. Thank you.
Mm-hmm. And then if we were doing non-QPSK baseband encoding, then these exponentials would be different things, right? They could be, if we're doing pulse amplitude modulation, then they would just be different real numbers. If we were doing 16 QAM, they would be one of 16 complex numbers, et cetera, et cetera. Okay. Okay, so the act of equalization is trying to undo what the channel has done. So that's kind of the big picture here for the rest of today. We are going to try and undo the stuff that the channel is doing. And for today's lecture, we are going to be assuming that whatever the channel is doing is a linear time invariant type of operation. Okay. Okay, so here is a rehash of what we've decided we are going to model the channel as. So we've got our symbols coming in at the transmit. And then we are doing, say, pulse shaping, and then channel distortion, and all that good stuff happens in H of Z. And then we're going to add in additive noise. And so this Z of n is the same as the last slide. And then this is the new business, is we are going to try and decide what kind of filter should we put between the decision maker. So this is the decision making, which for QPSK would be how much of the in-phase component do we have? How much of the quadrature component do we have? And take the SIG ends of those two quantities, and that gives you the quadrant of the symbol. And so this is going to be, again, our best guess symbol. Right? And if we're wrong, we get a symbol error, and if we're right, we pat ourselves on the back, and then we do it again 10 microseconds later, or whatever. Okay, so the idea is we want to implement a discrete time, preferably LTI filter, that takes our Z of n signal and cleans it up, and we're going to call the output D sub n. Okay, so this is a reminder from last slide. So from last slide. And so the first kind of equalization, the introductory version, is just called TSE. And it sounds a lot fancier than it is. It's called T-spaced because we are doing this thing in discrete time. And this is ostensibly just the symbol time. Okay. So when you hear TSE, just think, oh, we're doing 328, like discrete time stuff, rather than continuous time stuff. Okay, so, and then I'm going to apologize for the notation again, because the pedants among you, of which I consider myself one, will be alarmed to see this written in this way. Right? I hope you can tell me that that is not, strictly speaking, correct. Right? Because the Z transform doesn't multiply time domain things, it multiplies Z domain things to give you outputs in Z domain, and then we'd have to take an inverse Z transform. So what I mean in this line is the Z transform. So how should we do this? Z transform of that times these transfer functions, and the Z transform of this times the FC transfer function gives us the Z transform of D. And then the understanding here is that we're going to take the inverse Z transform of the result to get D of N. Okay, so this is bad. No, I won't say bad, because I mean there's a purpose for it. But this is sloppy notation. Like, I would get mad at my 328 students if they wrote that. Not mad. Yeah, no, mad, definitely. But I think so. I want to pause here, because if you're not comfortable with this sloppiness, it's going to give you hang-ups, I think, further on. So can I clarify what I'm talking about here? Like multiplying time domain things by Z domain things? I don't want to leave anyone in the dark, in the dust. I don't want to leave anyone behind.
Wait, so is that notation correct, or is it just
no? So,
okay, so it's
there is an implicit understanding that when I have this written, that either one of two things I'm hoping that you will read this as, oh, he means do all this in the Z domain and then undo the Z transform to get the time domain. And that's how I picture this when I read it.
okay.
But yeah, it is definitely sloppy.
Okay, thank you.
Sure. And maybe just for the first one, I'll write it out what it ought to be. So what it ought to be is split into two lines. D of Z is F of Z, H of Z, S of Z plus F of Z, W of Z, and then D of N is the inverse Z transform of D of Z. Right? That's what I actually mean in this line. So, but just to compactify things, I'm going to sloppily write time domain things times Z domain things, which I will freely admit, if you read it literally, doesn't make sense. But if you read it with a little bit of maturity, I think you understand what I'm trying to say here. Okay, so we've got the D signal, the signal that we're going to send into our deciding system, is the sum of two components, sum of two inputs. How the symbols get corrupted and then uncorrupted, and then what that uncorruption does to the noise. Yeah? So if I kind of lump the two F and H transfer functions together, right? So the product of these two things, we'll call that capital C of Z. Well, then what we've got here is the impulse response C of I. So if I inverse Z transforms this, so Z inverse gets me C of N, which I'm now going to write as C sub I, or C sub N. So what we've got here is the convolution. So now this is actually, this line is proper. This would make your 328 teacher happy, because this is a time domain operation plus another time domain operation gives us a time domain signal. Maybe they would ask you why you use brackets over here and subscripts over there, but whatever, get over it. Okay, so we've got the D of n signal is composed of two components. There is kind of the stuff due to the signal and the stuff due to the noise. And I want to decompose the stuff due to the signal even further. I want to decompose it into the stuff due to so this is due to symbol u. So I'm picking one index out of all infinity time indices, and I'm saying this is going to be the output at time n due to symbol u. And then if you do that, this is due to symbols not at time u, which is a long-winded way of saying these are inter-symbol interference terms. So this is a little tricky the first time you see it because we're using this index u that kind of came out of nowhere. But what we'll end up doing is we'll end up allowing for delays. Really, that's what this this u is supposed to allow for delays. And let me, if it bothers you, I think you are justified for the time being, whenever you see a u, replace it with a 0. Like, you won't lose a whole lot if you do that. But if you are comfortable with allowing for the possibility of a delay between the input of the equalizer and the output, let me try to convince you why that's a reasonable thing to expect. If we have a delay between the input here and the output here, that's a little bit like allowing for more information to accumulate before you make a decision. Okay? And that, when I phrase it that way, I hope you see that that's actually not a terrible idea. It's going to introduce end-to-end delays. Yes, I agree. There's no way we can delay here and then make that up later. So it will mean that if I send a bit at time instant t0, I will not get it at time instant t0 at the output. I'll have to wait some time to get it. But if the trade-off is such that I can get a better guess at what the symbol was, maybe I can tolerate a bit of delay. And that's what this will end up buying us, is if we allow ourselves to accumulate a couple of symbols before we start making decisions, then that will make our decisions better. Okay, so we don't know how many symbols to wait, which is why u is a variable. But the idea is maybe there is a non-zero amount of time we should wait before we make these decisions. Are you on board with that? Again, if that doesn't really float your boat, cross out all the u's and set them equal to 0. You're going to have a bad time on the very last slide, but for the time being, I think that's all right. Okay, so if we've got the symbol that we're after, the youth symbol, then all the other symbols are contributing to interference here. Okay, so now remember, keep your eyes on the prize. Our eyes on the prize are, we're trying to design f of z such that s sub n minus u is correct often, I will say. Right, because there is randomness, there is noise. We can't say anything for absolute 100% certain. But we'd like to design this f of z. And remember, designing a transfer function is equivalent to designing an impulse response, if we're talking about LTI systems. So either think about designing the filter coefficients or think about designing the impulse response taps. Those are equivalent ways of thinking here. But really, we're after the f, and the f is embedded in the c And so what we choose for F is going to pop up here, it's going to pop up here, and it's going to pop up here. Okay, so let's see one attempt to pick a good F. Zero forcing is the idea that, you know what, let's just kill off the ISI. The noise is going to be what it's going to be. Well, let's do everything we can to eliminate ISI, and then let the noise chips fall where they may. So if that is your approach, if that is the tack that you want to take, then you want to set the ISI term equal to 0. Yeah. So this is the ISI term from the bottom of the last slide. The only way to accomplish this would be, this means setting the ith C value equal to 0 if I is different than U, and set it to 1 if I is equal to U. Right? That would be the only way. If you had no information about the S's, and we only wanted to preserve the youth S, then this is the only way to do it. And so this impulse response, and remember this is the impulse response of C of Z, the filter that is the combined channel and equalizer filter. I was gonna ask you what kind of filter has a impulse response like this, but I think that I don't think I would know that if I was sitting in this class. So if you look into a table, this implies this kind of impulse response. C of Z is the Z domain transfer function that's just U delays. All right, so if that is the product of F of Z with H of Z, then that means that our equalizer filter is simply Z to the minus U over H of Z. And so if we do that, then, okay, then we get in the time domain that our decision variable is the symbol that we want. So we have accomplished our 0 ISI plus some version of the noise, where I am again being sloppy and mixing time and Z domains here. So I just want to drive home the fact that we are eliminating ISI and we're doing absolutely nothing for the noise. Whatever we do is going to be applied to the noise, and we're not really optimizing for that. Let me tell you why this is not a great idea. If this, so for starters, we don't actually know what the channel is doing. We don't actually have the channel transfer function. So I'm telling you that the equalizer filter is a function of something that we don't know. So that should probably not sit very well. But let's say that we could determine what H of Z was. H of Z, if you think about it in the frequency domain, in the digital frequency domain, is going to have nulls, probably, right? It's going to have frequency nulls. And they might be wide or they might be narrow, but not all channels admit all frequencies equally, right? Think about trying to transmit RF through a rainstorm. You are going to get, at certain frequencies, you're going to get all of your radiation is going to get scattered by the rain droplets, and you're going to get something that looks like a null at the at the frequency, what is it, the covalent bond of water, or whatever that frequency is. In a less kind of chemistry or abstract sense, if you have, what would be another example of this? If you walk from outside a building to inside the building, then all of a sudden the building is acting like a filter. And so whatever the building's made of, it's going to block the frequencies, say, that can't get through brick or that can't get through sheetrock or whatever. What you're going to end up having is you're going to end up having these valleys. And you might have other noise here or whatever, but what I want to focus on is these spectral nulls in the channel. Because when h of f goes to 0, h of z goes to infinity in terms of magnitude, which means that we are going to have this term at these frequencies is going to get huge. So we've eliminated the ISI, great. But by neglecting the noise, we have admitted the possibility that we are going to amplify noise at certain frequencies. So the very frequencies in which it's difficult for your signal to get through the channel are those frequencies where the noise is going to get amplified. And that's kind of a double whammy if you think about it. So not only is this signal going to be attenuated, but this signal is going to be amplified. So that makes deciding in the presence of noise really untenable. But if you have very, very small noise power, or if you have a channel that has no nulls in your frequencies of interest, this is not bad. It is guaranteed to give you 0 ISI. So there's that. Let's talk about something a little bit more nuanced. And it is not zero forcing t-spaced equalization, but minimum mean squared error t-spaced equalization, or I can't even do it. MMSE TSE. There you go. Alphabet soup. Morning, day, and night here. Okay, so what minimum mean squared error is we are going to try and build a filter. Again, we're still trying to design f such that the error is minimized in the mean square sense. Okay, that means I literally just shifted the words around in the sentence. But the idea is we need to somehow define the error, and the error will occur when this is non-zero. So this, if you like, is the error signal. It's when the deciding signal, d of n, is different than the decoded or the sent symbol. So this is what we want. This is what we have. So then the error is going to be the difference between those two. Okay, so what I've done here is I've kind of split this up. So I just copied the s of n minus u over here. And then these are the d of n terms from 2 slides ago. Okay, so we have the error defined in the time domain. Then let's talk about the mean of the square of the error. Well, that's if you just work your way from outside to in, here's the mean. So this E stands for expectation. And then the square is right there. And then instead of looking, because these are complex things, rather than just squaring them, we're going to square their magnitude. Okay, and then here's the error. Okay, so a little bit of a more difficult setup, but the goal is still the same. We're trying to design the F filter such that the D produces a very small error in the mean squared sense. So this is our new objective function, which we are going to try and minimize by intelligent choice of F. Okay. So if we just focus in on this part of the diagram, then the output d of n is the convolution of the input with the filter impulse response. And for the time being, we are going to allow this to possibly be infinite. Those of you who have a practical bent are going to be your ears probably perked up at that. Don't worry, we'll eventually curtail it to be a finite impulse response filter. But just for now, this infinity allows for a possibly IIR equalizer filter. Okay, so now we get into one of the reasons, I'll be honest, one of the reasons that I wanted to talk about this, and that is to go back to the orthogonality principle. So let me outline what it means in few dimensions, and then we can work our way up to more and more dimensions. So if we have something that we're trying to get to, so we want, say, the x vector, and this is our estimate, x hat, the best estimate is going to be the one that produces an error vector in which that is perpendicular. Think about if that were not true. So if I copy this diagram over here, if this is my estimate, if this is x hat, then this is the error, and this is longer than that. Okay, so this would be a worse estimate than this, than the picture on the left, because the error is larger. The error is longer, if you like. So let's see. I don't know if you're all with me here. So if we'd started this without the horizontal arrow, and the other thing is that we are assuming that we can't get into this space. So there is an assumption that we're trying to estimate x while stuck in subspace W. So trying to estimate x from subspace W. Okay, so that's where this is coming in. Right. So I don't know if you can see me, but if we're stuck in a plane and I want to get to somewhere outside of the plane, then the closest place in the plane is right below the place where I want to get, which has the effect of having that error vector being perpendicular or orthogonal. Okay. So in particular, if I were to pick a different estimate, say this one, then the resulting error vector, error 2, is longer than error, say, 1. And one way to know that this estimate is poorer, x hat 2, is the fact that this angle is not perpendicular, not orthogonal. Okay. Another way to think about this, if you're a geometrically inclined, is the closest point to a set is one in which if you drop a perpendicular, that is the shortest distance. Can I explain it again? Does anyone need it in a different way? Because this is a powerful technique. Go ahead, Andrew.
Yeah, could I try to, I guess, clarify or in my terms, I guess, in some sense, estimate kind of so you want x, obviously the x vector, and the estimate is kind of like you're trying to is like what what the signal sends out, not exactly what you want. And so the error is that error vector is the correction to x in some sense.
Yeah.
Is that how you can look at it?
Yeah.
Yeah. Okay.
So the error vector, just by how we defined error, is what you have minus what you want. So this is what you have minus what you want. And if you define it that way instead of the other way around, then you get this nice kind of vector addition that you can go from your estimate up by the error vector, and you get to the true point, if you like. And so the implications that this has for us is, because we are using linear and time invariant systems, we are only able to do linear and time invariant things to the data that we collect. And so because we are constraining ourselves to do only linear transformations on the z signal, that means that we are constrained to live in the space spanned by the z samples. And so that's where we're applying this subspace notion, is that we're only going to be living in the space spanned by the z's, but where we want to get might be outside of that space. Okay, because the noise might pop it out into a different, slightly different space. And so what we've got.
Okay.
Go ahead.
Oh, sorry. So like if you were doing like QAM, let's say like the QAM decoder, and could I actually draw on this like this? Did you see that?
Oh wait, over on the left. All right, yeah. Go ahead.
I don't know. I don't want to use that. And so like if you have your, let's just say, oh, that's really small. I don't know if you could see those dots.
I get the idea.
How do I, oh, here we go. Okay. Okay. And so if you have like a dot here, that's your estimate. And then getting to the point, would that be the error, like vector in some sense?
I see where you're going. I see where you're going, but that's actually, we need to expand this into the time dimension as well. So we're going to run out of room here. So think about this as a whole string of QAM points. Yeah, this is time going this way, and so what we are receiving. So let's say that we send this one, and then we send that one, and then we send this one, and then we send this one again. Say, but what we're receiving is something like this, and then this, and then this, and then this.
Okay.
So the error is going to be at time n, how far away is our decoded signal from the true signal?
Okay.
And the information that we have to make that guess, to make that decision, is a function of the x's only, not of the o's, right? We don't have access to what was actually sent. We only have access to what we received.
Oh, okay.
So yeah, it doesn't quite work to just think of this in the plane, because we have the time dimension as well.
Okay, that makes sense.
Cool.
Okay, that makes sense. Thank you.
Okay, so what I'm saying here is exactly the orthogonality principle. So remember, this is the error at time n, and I'm saying that has to be perpendicular or orthogonal to the received data in all previous times, because it's received data that defines the subspace. So z sub n minus 1, z sub n minus 2, those span the subspace W that we can get to, right? Because we can only get to places where the data suggests we can go. And if a vector is perpendicular to a subspace, then it is perpendicular to every vector in that space. That's the definition of being orthogonal to a space. So this is true for all past data. Right, so the subspace W is the space spanned by z sub n minus 1, z sub n minus 2, et cetera, et cetera. And what we're trying to do is we're trying to determine what d should we choose to minimize the error at time n. All right. And then if there's a notion of orthogonality, there must be a notion of inner product or dot product, right? So in this geometric space with vectors and arrows and stuff, then the notion of orthogonality and the notion of perpendicularity is one and the same. But just like we had in function spaces, we had to define what an inner product was, and then from that definition, we could use the concept of orthogonality. Likewise, in the space of random variables, we can define inner products. And so if I want to take the inner product between random variable x and random variable y, when they're random variables, we're going to talk about the expectation between x and y conjugate. So this is a little bit like covariance between x and the complex conjugate of y. If I say a little bit because you'd have to subtract off some means, but if you have zero mean random variables, then this is exactly the covariance between x and the complex conjugate of y. And I hope that notion reinforces orthogonality, or why this is a good inner product, because if two random variables are uncorrelated, then it would make sense that information about one doesn't tell you about the other. And so we have this idea that they are going to be orthogonal in terms of information content, if you like. Okay, so we're going pretty heady stuff here. When I say it out, when I wrote the notes, it wasn't that bad. When I say it out loud, I can see how this is going to be confusing. That's reassuring, isn't it? So what we've got here is the inner product. So this is the inner product between d of n minus s sub n minus u and z of n minus l for all these l's. And this interpretation, perpendicularity, means that these all have to be 0. Okay, so this is the orthogonality principle in action. We are taking all the data that we have, and we're saying that our estimate, or our error, if it's going to be the best error possible, has to be orthogonal to all of those data points. And the way that we are going to implement that is to take these expectations and set them equal to 0. Okay, so we got a little bit more room here. And the other, we're going to make some follow-on assumptions, is that the symbols that we send and the noise that we sample should be statistically independent. There's no reason to think, or for the time being, there's no reason to think that the thing that you're sending influences the noise that you see. And then also remember that the symbols are, we're going to assume that they are equally probable, which means that the expectation of symbol n is 0, right? Because the average of these 4 points is the origin, if they're all equally likely. Okay, so that's going to be also pretty key to simplifying what goes on down the line. So this expectation is, you can think of it as multiplying this and this, and then this and all of this. And so we'll do the second thing on the next slide, but on this slide, we're just going to focus on the expectation of these two. Okay, so what we've got here is the expression for z of n minus l. So what was z again? Z of n if we flip back here, is the S of n convolved with H of n, the channel, plus the additive noise. Okay. And so what I've got here is S sub n minus u times the first convolution. So that gives us this term, plus S sub n minus u times the noise term. Okay, so it's just a whole lot of distribution across addition. Okay, so I'm now going to capitalize on the fact that the symbols and the noise are independent. And if I take the expectation of the product of two independent random variables, then that is the product of their expectations, if independent, which means that this is the expectation of W star and the expectation of S, both of which are 0. And so that term goes away because the symbols are 0 mean, if you like. Okay, the H's are deterministic. So I can pass them in and out of the expectation without impacting the statistics. And so what I'm going to do is I'm going to hop the expectation operator inside the sum. Okay, so now I am looking at the expectation or the covariance of the symbol stream at two different times. And because those symbols are, we're assuming independent as well, that Sn is independent of Sm if n is different than m, right? This is another way of saying that across time, the symbols are uncorrelated or independent from each other. And that would be a reasonable assumption if the bits were random, truly random. So now we've got the expectation of the product of two random variables, which is, if they're independent, the product of their expectations, which is 0. Except when the indices match, right? So if n minus u equals n minus j minus l, well, when would that happen? That would happen when u was equal to j plus l. Yeah. Or another way, actually a better way to write this is j, because j is the index of summation here. J is u minus l. There we go. So for all other j's, this the summand is 0, but when j equals to u minus l, we get the covariance of the symbol. And what I'm going to do is I'm going to list that here. This is expectation of Sn star, which is the energy in symbol Sn, which is the energy in the symbols because they are equally spaced from the origin. Okay, so I want to drive that home that there are a couple of capital E's on the screen, and most of them are expectation operators, except for this last one, which is actually an energy measurement. All right, this is taking longer than I thought, but hopefully I'm bringing enough people along for the ride that it's worth it. Yeah, there's no way I'm going to get through 4 slides in 1 minute. But the risk I'm taking is that we're going to go have the weekend now and that everything's going to be lost. So can I just preview what's coming next? All right, yeah, this is a fine place to break. So what's coming next is we do the other term, the other part of this expectation. But I will reset the stage for you on Monday. Thanks, everyone.